a study of randomness within the S model. We begin by examining the relative sizes of gap-type covariances. Every gap has a left and right neighbor. For example, the sum of twins is the second minor primorial. We can rewrite this as the sum of twins and their neighbors, which summing to some local maximum we get that the second minor primorial at M must be the sum of all the twin covariances at that M. That is, we're adding the number of twins, given all the possible neighbors, on either side of each twin. We already know how to count some of the pairs, since the count of atomic pairs goes as the third minor primorial. We have our second minor primorial equals twice the third minor primorial, plus some trailing terms, or, dividing everything by the second minor primorial, we get twice the ratio of primorial minors, plus trailing terms, must equal 1. Which for large M becomes 1 equals about 0.18, plus trailing terms. That is, over the entire set of the primes, if you find a twin gap, it is paired with a cousin, about 18% of the time. All other pairings, through infinity, must share the remaining distributional space. Not only is the induced PMF fat-headed and long-tailed, but so are all of its covariances. How random is SM? Given that we can exactly predict at least the count of twin gaps, we can ask what would happen at some M if instead of the composites being kicked out rationally, it went haywire, and the members kicked out were chosen randomly. At some M, we have our second minor primorial of twins, from a collection of our first minor primorial of gaps. We make our next primes copies, and randomly choose our first minor primorial, pairs of gaps, to coalesce into new gaps. Twins can only be eaten, and never born during coalescence, so the count in the next generation is expected to be. We want to compare what happens if the existing space in random versus natural models. How big would the error be? Apparently almost indistinguishable. That is, the S model approaches a uniform random behavior as M becomes arbitrarily large. Now recall, we can order each iteration by examining the residuals. In each case, the larger index set is missing the mth prime relative to the smaller index set. That is, given Gm, the set of gaps in Sm, we say the set of its ordered subsets is open for all larger index sets, and closed for all smaller index sets, in the sense that earlier gap sets can cover most, but not all of each model. For example, the first step in constructing the next set is building an X-prime copies of Sm's gaps. This is followed by consuming a first minor primorial sets of pairs to create our first minor primorial new gaps. This will always create new gap types which cannot be covered by older rules. That is, each SM can accurately describe a number vanishingly close to 1 parts of the next iteration. So the degree of self-similarity comes arbitrarily close to 100%, as M becomes arbitrarily large. But it is also recursive, such that given we understand SM, its knowledge of some index distanced k away is the ratio of the relative logs. Realistically, we can never have very much knowledge, because the sets grow too quickly. But knowing that first little bit does at least begin to describe a portion of about 1 in log p. A final note about compressibility. Though we talk about this in greater detail later, the season number theorist should have already sensed the correctness of the Hardy and Littlewood conjectures. We simply wish to discuss this while on the topic of randomness. The algebraic constants for the various gap formulas describe the local density, and due to Hardy and Littlewood, we learned we can translate them to simpler forms via some number divided by the log for some gap strings. This means any compression algorithm becomes worthless for large enough x. This is because it will always happen that eventually it will cost more to maintain the lookup table than it can deliver. Whatever the particular sequence you wish to store differently, it will always become rare enough not to bother, because the available table of prime gaps grows without bound. This ends our brief introduction to the S-model. Intermediate videos will probe deeper to find the local maximum gap, identify a substructure of both the S-model and the primes, called the backbone. We will also prove various conjectures by Legendre, Polignac, and Hardy and Littlewood, and find a new form of Chebyshev's function. And we will prove Riemann's zeta conjecture. For more information, please see our intermediate lectures, or Google multiplication modulo n along the primorials, with its differences and variations, applied to the study of the distributions of prime number gaps.